The primary empirical objection to quantum consciousness is the timing gap. Neural superpositions decay within femtoseconds, yet conscious decisions take hundreds of milliseconds to manifest. For 20 years, this discrepancy in scale has made quantum models of the mind appear physically impossible. While the physics of decoherence is accurate, the temporal framework we apply to it is likely misplaced. The unfinishable map proposes that consciousness operates after decoherence, selecting from an already decohered mixture of states rather than attempting to maintain a fragile superposition. By shifting the point of interaction past the decoherence event, the femtosecond timescale loses its power to invalidate the theory. The options are already on the table before the mind makes its choice. This research program builds a biologically sound architecture through 5 converging lines of inquiry, from quantum Darwinism to stochastic amplification. The timing gap is a byproduct of looking for the interface in the wrong part of the sequence. Decoherence suppresses quantum interference, giving the brain a stable, classical appearance. This produces an improper mixture, a set of possibilities without a specific outcome. This leaves the problem of outcomes. Physics explains the menu, but lacks a mechanism to explain why one state becomes reality. A non-physical principle of consciousness fills this physical gap, acting as the final actualization mechanism. We proceed on the basis that physical selection is a genuine singular event. In this framework, one outcome survives and the others do not. The outcome gap is the structural void where the conscious interface operates. Selection is not an act of arbitrary magic. The mind is strictly bound by the information provided by its environment. In quantum Darwinism, the environment redundantly encodes information about possible states. This environmental monitoring selects which states are robust enough to survive. This fixes the menu of options. Consciousness must respect Born-Lowell statistics over time and operate within the classically distinguishable states the environment has prepared. This selection is also limited by the internal structure of the brain. The Cochin-Specker theorem shows quantum outcomes depend on the full measurement context. In neurobiology, the physical configuration of synaptic vesicles and ion channels defines this geometry of choice, shaping the available pathways for action. The conscious interface is caged by the menu of the environment and the physical architecture of the neural system. Most models assume consciousness must trigger a sudden, localized collapse in the present. A different mechanism emerges within the two-state vector formalism, which describes quantum systems across time rather than as a single moment. This framework uses 2 state vectors, one evolving forward from the past and a second evolving backward from a future measurement outcome. Experiments in weak measurement confirm that these future boundary conditions shape what is physically real at intermediate times. Because consciousness provides the target state, the goal or intended action, it can be modeled as the source of this post-selection boundary condition. Rather than pushing the system from the past, consciousness specifies the target state, and the neural history converges toward that destination. Operating as a boundary condition places conscious selection outside the chronological sequence of the brain, bypassing the timing problem entirely. We must account for this intervention scale. A quantum bias involves energies 1 trillion times smaller than the signal needed to fire a neuron. Bridging this 12 order of magnitude gap requires a 3-stage biophysical amplifier. First, stochastic resonance allows thermal Norenzepa synapse to push a weak quantum bias over the molecular detection threshold. Next, self-organized criticality allows the synaptic signal to trigger cascading avalanches that span whole neural networks. Finally, threshold crossing dynamics accumulate this bias until one specific action wins the race to a macroscopic decision. The brain appears to have evolved an architecture that exploits thermal and synaptic noise as a signal carrier, amplifying microscopic intentions into macroscopic behavior. This complete architecture maps the journey from the quantum outcome gap to the macroscopic threshold. It integrates a specific locus of action, a temporal boundary mechanism, structural contextuality, and a 12th-order amplification pathway. The model upholds the irreducible nature of consciousness while respecting the limits of minimal physical interaction. Current technology cannot yet provide an end-to-end empirical observation of this entire chain. However, the components create a web of mutual constraint. Each link in the chain narrows the requirements for the others, driving the research program toward higher specificity. The timing gap is a misinterpretation of the sequence. Once corrected, It reveals a mathematically precise interface where the mind commands the machine.